What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 6, Practice Test. Let's do it. So for number 1, it's asking to the nearest whole number, what will the population be after 3 years? So what we're going to do is we're going to plug and chug, plug 3 in for t. So now that we got this, we're going to evaluate it in a calculator using Desmos. So when we multiply it out, we get 12.8, rounding to the nearest whole number, gives us 13 dolphins, boom. Drew wants to save $2,500 to go to the next World Cup to the nearest dollar. How much will you need to invest to now with 6.25% interest compounding daily in order to reach his goal in 4 years? So let's set it up. So A equals P times 1 plus that interest rate in decimal format, which is 0.0625 over, when it says compounding daily, that means 365 times per year. So that's what we put as the denominator, raised to the same n value, 365 times t. Now, what this is asking is, what principal do I need to invest in order to get 2,500, that's my A value, in 4 years? So I plug in 4 for t. So what I'm going to do is I'm going to plug this value into the calculator and see what we get. So we get approximately 1.28399. So we're just going to round that to 4 there, and then we got that times p equals this. Last step, we're going to divide both sides by this constant, and we're going to see what we get in the calculator. So when rounded to the nearest dollar is $1,947. So that's how much you'd have to start to invest with. Boom, done. So for this question, we're meant to graph this and its reflection across the y-axis. So first, let's graph this exponential function with a couple values. Now you notice it's to a negative x value. So normally an exponential will look like this, but we've got a value in here that's less than 1, which means it will go like this. And then it's reflected across the y-axis because of that negative. So that means we're starting with something that looks like this. Now we can get a couple of nice values that are easy to graph. For example, plug in 0 for x into the f function, and we get 0.5 to the 0 power, which is 1 times 5, which is 5. And we can also plug in maybe positive 1. So 0.5 to the negative 1 is 1 over 0.5, which is just 2. 2 times 5 is 10. So you can see that when you plug in 1, you get 10. And then also when we plug in negative 1, negative 1 would be 1. 0.5 to the 1 power is 0.5 times 5 is 2.5. So that's when x is negative 1. So this kind of matches up with what we would have expected, and it's going to kind of go like this. And the reason why I know that is because this is never going to go into the negatives or even below 0, right? Because you have a positive value. Even if we raise it to a super negative value, that's going to go close to 0. So that's going to be this function. Now, when we're talking about a reflection, we're basically going to have the same y-intercept, but then this value here is going to be reflected. This value here is going to be reflected like that across the y-axis. So you can see that it's going to look something like this. And just so you can see what the reflection would look like, remember I mentioned that negative reflects it across the y-axis. So the reflection of this would be to negate that again. So it's just 5 times 0.5 to the positive x, and that would equal the reflected f of x function. And that's how you do it. Done. For this one, we're going to write this as an exponential equation, and we're going to start by taking the base of the log. We're going to raise it to the power that's on the opposite side of the equal sign, and we're going to set that equal to this argument. And that's all you got to do for number 7. Boom, done. So for this one, we're going to start by converting to its exponential form, and we're taking that base, 1/7. We're raising it to the power, which is on the other side of the equal sign. So it's 1/7 squared equals that argument, which is x. So what is 1/7 squared? That's 1/7 times 1/7, which is 1 over 49. That's how you do it. Done. So for this one, we're going to evaluate using a calculator. So let's plug into Desmos. So this equals roughly negative 0.334. So negative 0.334. Boom. Done. So for this one, we're meant to state the domain, vertical, asymptote, and end behavior. So first, let's start with the domain. Now, the thing about a logarithmic is the argument always has to be greater than 0. So literally, we can start with that. This argument must be greater than 0. By isolating x, we'll get the domain. So first, I'm going to subtract both sides by 39, and then I get negative 13x is greater than negative 39. Then we divide both sides by negative 13. Flipping the inequality because you're dividing by negative, and that's x is less than 3. So this is my domain right here, but that's also the starting point of our vertical asymptote. Its x is always going to be less than 3, which means we have a boundary at x equals 3. That's the vertical asymptote. So now we're going to look at the end behavior, and we're going to look at it in 2 spots as it approaches this vertical asymptote of 3, and as x gets really, really small to these massive negative numbers. And the reason why is because that's where it continues off, right? It's starting at 3 and then it goes super negative. So that's going to be our end behavior. It doesn't exist when values are greater than 3. So it doesn't make sense to say, hey, what's the end behavior as x approaches positive infinity, because it doesn't exist past 3. And by the way, this function, since we have a negative in front of that x, like a normal logarithmic would look like this, but negating the x actually flips it across the y-axis. So now it's going to look like this. And here would be our vertical asymptote at x equals 3. So we're saying as x approaches 3, and in this case, we're approaching it from the left, right? It doesn't exist to the right. So we say as x approaches 3 from the left, the function value is, it sure looks like it's going to negative infinity. So the function value is approaching negative infinity. Then the other way we say it is as x approaches negative infinity, meaning as we go to the left, well, it looks like it's going up and up and up. So the function value in that case is approaching positive infinity. So that's how you do it. Boom, done. So this one we want to rewrite in compact form, and the beauty of it is that since we have the same base for the logarithms, when we're subtracting, it's like dividing the arguments. So this is the same as log base t of 96 divided or over 8. What is 96 divided by 8? That is 12, so we can write this as log base t of 12, boom, done. For this one, we're going to expand with the logarithm in arguments inside, remembering that multiplication is like breaking this up into plus, right? So I can say ln of y cubed, and then since it's y cubed times z squared, I can break it up as ln of z squared. And then again, I'm multiplying by that cubic root, so I can break it up as plus ln of the cubic root of x minus 4. So this is a good first step. Next, I'm going to use my power rule of these exponents that allows me to bring the 3 in front and the 2 in front as nice coefficients. And before we deal with this, we want to recognize that a cubic root is really the same as raising an argument to the 1/3 power. And knowing this then allows me to bring this down as a coefficient. So it's 1/3 times this, with the final answer of 3 ln y plus 2 ln z. And multiplying by 1/3 is the same as dividing by 3. So I could also write this as ln of x minus 4 over 3. And there you go, fully expanded, done. So for this one, we're rewriting as a logarithm. So I always say log base, and the base is the same as this value that's being raised to an exponent. So it's log base 16, and then it's of, the argument is going to be what's on the other side of the equal sign, 1,000, is going to be equal to that exponent of 3x minus 5. Now they want us to use the change of base formula, so I will use it, but you don't really need it when you're using Desmos. But it's basically log base 10, which I'll use because it's easier to write in a calculator, of the argument, the big number of 1,000, over log base 10 of that base, which is 16. So let's approximate this in Desmos, and we get roughly 2.491. And now we're going to isolate just by adding 5 to both sides and then dividing by 3 like so. And let's see what we get in the calculator. And then we get this nice value of 2.497 to the nearest thousandth. So x equals approximately 2.497, boom, done. So for this one, we're meant to solve. So first I'm going to do my basic isolation. I'm going to start by adding 5 to both sides, and I get negative 9e to the 10a minus 8 equal to negative 41 plus 5 is negative 36. Then I'm going to divide both sides by negative 9, and I get e to the 10a minus 8 equals 4. Now I need to bring this exponential variable down, and I'm going to do that by using logarithms. Since I got a base of e, I'm going to take natural log, just going to be easier. This allows me to bring the exponent down using my logarithmic properties. And then it's times ln of e, but ln of e is 1, so that's really nice. That's why natural log is good here. And then this equals ln of 4. Next, I'm going to add 8 to both sides, like so. And finally, I'm going to divide both sides by 10. Now, since it says find the exact solution, we're not going to approximate in Desmos. It's just natural log of 4 plus 8 divided by 10 equals a. Boom, done. For this one, we're going to start by isolating the variable. So we're going to start by adding 4 to both sides, and then we get negative 5e to the negative 4x minus 1 equals positive 68. Then we're going to divide both sides by that coefficient of negative 5. So I'm going to get e to the negative 4x minus 1 equals negative 13.6. Now, at this point, I need to get this down, right? And the way to do that is to take log, or specifically because we have e, it's going to be easiest to take natural log. But we have a problem because you can't take a logarithm, whether it's natural log, log base 10, you can't take it of 0 or a negative. So this is outside of the domain, which means we're stopped in our tracks. There is no viable solution, which means this is no solution, or we can write no solution as they asked. So that's how you do it. Done. So for this one, we want to start by recognizing that this is a quadratic in disguise. So you want to treat this as just like if you had x squared minus x minus 72, and you'd start by factoring. So how would this factor? You'd say what two numbers multiply to negative 72 and add to negative 1, right? That's the coefficient there. So that'd be positive 8 and negative 9. Now, instead of putting x and x here and here, instead, we're going to think of the two things that would multiply to give us e to the 2x, which would be e to the x, right? Just that middle term. And now we got two different equations we can make, right? We're trying to figure out when this goes to 0, because if this goes to 0, it's going to 0 everything out. And we want to know when this goes to 0, so we're setting this binomial equal to 0 as well. So let's solve this one first. We're going to add 9 to both sides. Then we're going to take the natural log of both sides to bring this x down. And then x times ln of e is just x, because ln of e is 1. So we get ln of 9. And that's a nice exact solution, so we're not going to do anything there. Now for this one, we're going to start by subtracting 8 from both sides. Now we would take natural log normally, but because we're taking natural log of a negative, this is not a viable solution. You can't take a log, natural log, log base 10. You can't take any of those of 0 or negative. So this is not going to yield a viable solution. So the only answer is this, ln of 9, boom, done. So for this one, it says use the one-to-one properties to find an exact solution. And we're going to start by using our nice property that says when we're adding the same logs, we can just multiply their arguments. So this becomes log base 10, because there's no argument, right? But then we can assume it's 10, of 3 times 4x squared minus 10, which is 12x squared minus 30, right? We're just multiplying and distributing, equals log of 51. And once we get to this point, we know that these arguments can be set equal to each other without the logarithms. So we have 12x squared minus 30 equals 51. Let's add 30 to both sides like so. We get 12x squared equals 81. We're going to divide both sides by 12, and we get x squared equals 81 over 12. This can be simplified, dividing top and bottom by 3 to 27 over 4. Now I can take the square root of both sides, and I get x equals plus or minus, and then the square root of 4 is 2. The square root of 27, well, 27 is really 9 times 3. So I can take the square root of 9, which is 3, and then that square root of 3 stays trapped inside like so. And then when it comes to the plus or minus, are both solutions viable? Is only one viable? Well, since we only have one x in here and it's being squared, the negative and the positive are going to give the exact same result. So they must both be viable solutions. There's no violations going on in terms of like taking the log of a negative. So my two solutions are plus or minus 3 red, 3 over 2, boom, done. So this one, we're going to start with our baseline exponential equation using e as a base. So it's y equals a e to kt, right? And k is some constant that we have to figure out. Now, a is my initial value, which I know is 112. Now to solve for this k value, I've got another nice pair of values. I know when t or time is 17 days, we got 80 grams left, and that's y. So let's plug and chug. So then we're going to divide both sides by 112. And then when we get to this point, to bring this down, we need to take the natural log, or any log really, but natural log is best because we got base e. We need to take that at both sides, and that allows us to bring the exponent down. So that 17k comes down, multiplies ln of e, but ln of e is 1, so that's beautiful. And then we got ln of 80 over 112 here. Last step, we're going to divide both sides by 17, and we're going to get a value for k. So we get negative 0.019792. So now we can write this equation out as y equals 112 e to the negative 0.019792 times t. Now we're trying to figure out the half-life. So I want to know when y is going to be half of this initial value, right? That'll give it to us. So what's half of 112? That's 56. So now I got this nice equation. Let's solve for t. So first I'm going to divide by 112. 56 divided by 112 is 1/2. Now to bring this variable down from the exponent, I need to take log. In this case, I'll take natural log of both sides, right? And that allows me to bring this down as a coefficient. And again, ln of e is just 1. So now I have ln of 1/2 equals negative 0.019792t. And then we're going to divide both sides by this at the end to get our value for t. And we get this as our final answer, which is about 35. So the half-life is roughly 35 days. So there's your answer for the half-life. Here is your equation right here. Those are your two answers. Done. So for this one, we're meant to use Newton's law of cooling. So we're going to start with that formula, which is T equals, and first we have the temperature of sort of like the environment, which is 35. That's kind of going to be added on at the end. And then we take the difference of these, right? 71 minus 35, which is 36. And then we've got e to the kt like so. And we have to solve for k. So the way we're going to solve for k is we've got this. It says that after 10 minutes, the internal temperature of the soda was 63. So 63 equals 36 e to the, it says 10 for t, so 10k plus 35. Then we're going to subtract 35 from both sides, and we get 28 equals 36e to the 10k. Then we're going to divide both sides by 36. And then once we have this, we're going to take log of both sides, in this case natural log, and that's going to help us bring this down, right, using our properties of logarithms. And then ln of e is just 1, so this is great because now we get 10k equals ln of 28 over 36. And then last but not least, we're going to divide both sides by 10, and we get ln of 28 over 36 divided by 10. And let's plug that into Desmos to approximate. And we get roughly negative 0.025131. And there's your equation. And then now we need to figure out what will the temperature be after 1 hour. And again, T is represented in minutes, right? That's what we plugged in here. We plugged in 10. So for 1 hour, that's 60. So we're going to plug and chug, and let's see what this equals in Desmos. So when we plug everything in, and I didn't round here, right? I just kind of put the whole thing in unrounded, or at least the amount of digits shown, and we get roughly 42.96958, which will round to the nearest degree to 43. So T equals approximately 43 degrees. That's how you do it. Done. So for this question, we're going to start by plotting this in Desmos, and then we're going to take a guess here to see if this would represent linear, exponential, or logarithmic. So let's do that now. So when we kind of plot these out, you see it definitely looks logarithmic, right? It kind of goes up, and then you see it flattening out like that. So I would absolutely say this is logarithmic. Boom. Done. So for this one, we're going to start by plugging it into Desmos. We're going to identify whether it's exponential, logarithmic, or logistic, and then we're going to apply the correct regression. So once we kind of plot out the data, it definitely looks exponential to me, right? It's kind of going up. It doesn't seem to have a top point where it levels off. So this is not logistic, and I would say it's exponential. So the way we run the regression in Desmos is by plugging in this, and sort of these values are generated. And so let's write it out. So we got y equals, and then we got this constant a, which is 15.1006. And I know they said they wanted 5 decimal places, so the fifth one would actually be 2. It just didn't show us in Desmos. And then our b value is 1.24621 raised to the x power. So this is how you do it. Boom. So for this problem, once again, we're going to plug the values into Desmos. We're going to see, is this exponential, logarithmic, logistic, etc. And then we're going to run the appropriate regression. So let's do that now. So for this one, as we map it out, you can see it kind of goes up, and then it kind of slows down in terms of the slope, right? It seems to be leveling off. So this definitely looks like a logistic function. So now let's run the appropriate regression model. So here's how we run the regression for a logistic model. And look how nice and perfect that looks. So here are the constants for the logistic model, so let's write them now. So as I mentioned, we are choosing logistic for this, and then now let's write it out. Y equals, my a value is this, but they want it to 5 decimal places, so it's just 18.41659. It just only rounded to there in Desmos, but that's what it actually is. And then we have 1 plus 7.54644 e to the negative 0.68375 times x, and that's how you do it. Boom, done. I hope you guys enjoyed this video, and if you did, please click that like button, and if you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.